Great. So today, we have three speakers rather than one. Actually, we have four speakers, except one is missing. And these are the students who did the Everest project and the Guided Team Challenge. And so they're going to talk to us about the impact of changing water availability patterns in public forests. So it's going to be a team presentation by Felipe and Gihan and Giovanna. So, all right, Roger.
Thank you, Keshav. So Keshav introduced us. So Felipe, myself, Giovanna, Ihan, and Onkar's not here. So just for people that are not familiar with AR4ER, this is our first assessment that we have to do, the risk rated. So they gave us like a research question and we have to solve it in some way. So always it was entitled Assessing the Impact of Droughts on Tropical Forests. And we were helped by a lot about Amelia and Charlotte. So thank you for both of you. And so we'll start the presentation now. So the big question that we want to address, like in our job, in our work, it was what are the effects of changing water availability patterns on tropical forests. But before talking about this,
there's no video on Zoom for some reason, but you see the screen is black.
Oh,
On the Zoom screen. I don't know if anybody's on Zoom. Michael, is your getting a blank over here?
Oh, it says that orange bar says some things about sharing screens pause.
Oh, yeah.
Sure. Yeah.
Green button now.
Yeah.
Yeah, review.
Mm.
I don't know.
How dare you?
I don't, let me try to share again.
Maybe when we present, yeah, for whatever reason, when you share the screen, then it goes off.
But I was seeing what I'm showing there, so it doesn't make sense.
No, that's fine. We just video wasn't
Huh?
going. No, the screen was being shared, but the video was
The
not.
video was paused.
Now I cannot. It's everything breakdown. Okay. Let's try it again.
Okay, we can see now.
Is it working?
And you can see us?
Yes,
Okay.
Cool.
thank you.
Okay. Sorry for that. So yeah, so going back again, so we want to address this question, what are the effects? But before telling this, we want to convince you why it's important for caring for tropical forests. I think most people here, you're already convinced about this, but like, let's pass through this very fast. So tropical forests are important carbon stocks. They also help a lot on climate regulation. And also they held and they contain like most of the land species biodiversity that we know. And they also provide national and local and to regional economic benefits to people. However, they are threatened, and we can see this by an increasing trend of tropical forest loss happening in the last few years, which has not decreased yet, or it doesn't look like seeing to get to the most, like it's decreasing in the near future. So what are some of the drivers of the forest loss? So the biggest one, and what we are most concerned about, is deforestation. And deforestation itself, it also contributes to climate change with other sources we know. And climate change by itself led to other things that can cause forest loss, like extended dry seasons, frequent higher severity droughts, increased wildfire risk, or spread of invasive species. And some of them, they also call the feedback loop on climate change, that for instance, like keeps feeding this and increasing forest loss. And for this work, we were focusing on two of those effects, is the extended dry seasons and also the frequent and higher severity droughts. So to be easy to address this question, because it was like a very broad research question, we divided in three research subtopics. So the first one is how forest structures are determined by typical water availability. The second one is how the forests change in a climate spectrum of different climate variables. And the third one was how the forests they handle what happened then when they are exposed to anomalous drought effects. So for analyzing this, we took places in South America, in the Amazon region, and the other ones. So you can see from region 1 to 8, you have a gradient of precipitation, where the first one you have a lot of rain, and the last one you have less rain. So it's a clear decreasing precipitation gradient. And so, as I said, from the region 1 to 5, you are in the Amazon moist tropical forest, while on the 6 to 7, you are in the seasonally dry tropical forest. There are parts in, most of it is on Cerrado, but we have parts on Caatinga and Atlantic rainforest as well in these other 3 polygons. So I'll first give a data description and pre-processing we did for getting the results we are showing in the last part of the presentation. So if our job was a movie, probably GEDI will be the superstar from our movie. It's the most important part of the data that we are using. So GEDI was designed for pantropical ecosystem applications. It's a full waveform LiDAR. So if you look on the left side of the slide, you can see how is the raw output of GEDI. So you have this waveform where it's proportional to what's coming back from the sensor that it was emitted. And from those curves here, I will show a video afterwards to understand better how this data is sensed. But you can extract very important forest key metrics like the canopy height, the plant area index or PAI. We'll talk a lot about this, so I'll give a definition. So plant area index is the area of plant divided by area of ground. So you have a PAI of 3, you have 3 times the area of plant than you have in the ground. It's fine. I hope everyone understand that. And vertical PAI, because GEDI is an active sensor and the way it sends the data, it's possible for you to have vertical measurements of those parameters. So like this vertical PAI, you can have from the ground to the top of the canopy in 5 meter slice, you can have a measurement of PAI, which is very important for understanding how, sure.
Listen to PAI, so is that the plant area projected onto horizontal plane?
Yeah. Yeah. That's correct. And like so PAI is basically, some people, I don't know if you heard about LAI, which is left area index. For tropical forests, there were some papers showing that it's almost the same, it's 97%. So you can compare PAI is the same as LAI, because I think most people that read papers on ecology, people use a lot of LAI, but it's almost the same. But this is including other parts than leaves like branches and other parts of the forest.
Is that true for seasonally dry as well?
For seasonally dry, I don't read this. I don't find any comparison, but like I'm sure for tropical forests, it is almost the same. Yes.
Felipe doesn't read about dry forest, so.
Yeah. And just for the GEDI footprint is 25 diameter, so it's like this round, and you have the sampling for this region. And I'm showing a video here that I'm happy if it works. So if you have any question about this, please answer me and I will stop and to everyone be on the same page for understanding. So GEDI is on board of ISS, and ISS has a lot of instruments. One of them is GEDI, which is going to show in some instance.
How did you film?
I mean, NASA did, they're incredible. So
This was pretty much two months of our project.
yeah. So if you look, if you look to GEDI has, so these are the 3 lasers that are sampling. So to this one, they are full beams, and this one is coverage beams. So the difference between them is those they are sampling on full power, and those are sampling on half the power of those top ones. So the energy that is emitted by the top ones is stronger, which have some difference in the forest cover that I'll explain a little bit. But what's important to say that the one that are full power, they are more precise than the others that in half cover, especially for tropical forests, which is important for some of the filtering steps we did afterwards. So it's sampling, you can see the difference of the sampling. So this you can see there is more light. Those are the full beams, and those are the coverage beams. They are in less red than the other ones. So you can see there is sample in these patches, and I think it's 600 meters separated each of one of those patches, and it's 4.2 kilometers SWAT. And how GEDI sample? So it will emit this energy from these lasers, and this laser will hit the trees and will come back and measure. So it's measuring time actually. So you're emitting a laser, and you don't care about, like the other optical sensors, you're waiting for having information about the wavelength. But in GEDI, you don't care about the wavelength. You care about the time that it takes from getting out of the sensor, traveling to the Earth and coming back. So it's measuring time, and from the time you can derive distance from this. So that's what the sensor is measuring. So then you have these footprints that is proportional to how many of those photos are recorded back. So you can see that the ground return is the last one, and then the other ones, that's why you can have information about the under canopy. And on the top canopy, you have like most of the returns. So that's how you extract the information. You take part of those returns, and then you calculate because they're proportional to biomass and other biophysical proportions.
You did in the previous slide, it was like a continuous beam. How do you distant a reflection from one shot, kind of like, are the shots kind of spaced out enough so that like you don't see the top of another, but the next one and hit the ground, the last one?
Yeah, so actually they are not, so what they show is looks like it's continuous, but actually it's pulse of energy because the sensor, it doesn't have the energy for like keep on continuous pulsing. So you'll give a pulse and then we'll come back. So like if you look here, how they are showing, it looks like it's sampling on a continuous way, but actually you have like shots. It's like have footprints. You have some footprints. So you have a footprint and then 60 meters later, you have another footprint and then 60 meters later, another footprint. So it's emitting pulse and then this pulse returns and recorded. It's okay. Everyone understand this part? Okay. So yeah, I hope it's more clear how GEDI works so we can continue with that. So how we did the GEDI filtering? So GEDI comes on a very tricky way, the data. It comes on these granular formats that is like these long lines. And when you download it, you can just download the whole granule, even though if you want to work with this small region. So if you ask like you give a region and if there's one shot inside this region, you get the whole granule. So you have to download everything on your machine and then filter which shots you want. So this is like very tricky. Hopefully Amelia have developed everything for us. So she helped us on this spatial query. Thank you, Amelia, for that. And the quality control. So after we did the filtering, we have to be sure, especially for the Amazon region, that we have high quality shots and not like using every shot we had. So first we did PAI greater than 0, because if it has less is like 0 is because you don't have forest there. So we're not interested on those pixels. We also did sensitivity one. So since GEDI was designed for sampling only forests with less than 95% of coverage, so everything that is up than this was not supposed to, you cannot trust the data. So this is the parameter, is the maximum that it can reach. So we just take this to be sure we have sensible, the best shots that we might have, because we can have problems with the sensor that can reduce the sensibility. And also the full power, because as I said, this energy, you have to be sure that you are just using the energy that is the one with full power, because it can penetrate to the high dense canopies. And that's why in tropical forests, we want those with full beams and not the coverage beams, because the coverage beam, if you have like a very dense forest, you won't get to the ground. So you don't have very trustful data. And we use the definition of forest to exclude everything that has a cover less than 30% and height. It has to be bigger than 5. So the other one was excluded. Sure.
Yeah. Sorry, I guess I'm still a bit confused about what sensitivity means. Does it what does it mean?
So sensitivity is a kind of a measure of how much of the beam was high quality. So it also gives like an understanding of how much it can penetrate to the canopy. Because if you have a cloud, if you have something that is interfering, you will lose the sensitivity and you cannot trust the shot very much.
So does it mean that you get the waveform from the top of the canopy to at least like 95% close to the ground, something like that?
My understanding was that if sensitivity is larger than 0.95, that means that it can penetrate forest whose canopy is 95% covered.
Oh,
Yeah.
95%.
Yeah.
That was
Precisely.
so that's why we selected for only highly beams that had high sensitivity, which means they could penetrate these dense canopies. Yeah.
And the last one was land filtering. So we took map biomes of 2021. There is land map cover, and we selected, so where GEDI shot lands, we want to be sure that it was forests or savannas, and also a window of 3x3. So we are looking to these regions to see like if everything around and the shot was the data we were interested in, because we didn't want to take regions that were the forests or had another impact. We must be sure that they were forests in the time we were doing the analysis. So after this filtering, we have like 8,300,000 shots that we use it for further analysis. The second thing we use it, so for doing our analysis, we have to aggregate in monthly data. And we had some problems that I will show in a moment that we need to interpolate the data before running the analysis. So this region is region 2 for the month of March, April, and May. So these plots here is the spatial extent. So you have latitude and longitude, and those are the histogram of PAI. So there are two things that are important here to say. So here is the spatial coverage. So spatial coverage is how much of the area that we were analyzing were covered by GEDI sample in that month that we were looking. And we also have the temporal coverage, that is how the spatial coverage change in different timestamps. And we can clearly see that when you change this parameter of spatial and temporal coverage, you have difference on the biophysical parameters. But those we hypothesize that is not an effect of looking to the forest, it's not a change in the forest, but more a change in the sampling strategy. So we want to eliminate these effects because it's not what we're trying to see. So you can see like this is just because you have less shots and in different regions, you have a reduce on PAI. But when you go back to like almost the same amount of shots and cover a bigger region, you have again comparable PAI in the different regions. So we want to filter those effects. So here's like all the regions that we had and all the data for all the months. So here you have PAI on the Y, and here you have monthly timestamps. So look at this region 3. There are months that you don't even have data. And then this is probably do cloud cover, because GEDI cannot sample with dense cloud cover. And the other problem was like here, as I show you on those graphs, when you have high PAI and then you have a month with less shots, and then you have this decreasing, and then you have increase again. So basically pass a smoothing window for removing these effects and making the data more smooth and reducing those probably spurious effects we see in the data. Finally, we went to the climate variables. So from MODIS, we extract surface temperature, the fraction of photosynthetically active radiation. So F bar is the fraction that was observed by is the fraction of the radiation that can interact with plants. So plants can react just a part of the radiation, and we're just selecting for this wavelengths, and the other one we are not considering. And the potential of transpiration also for MODIS, and from the European data set, we had the surface net solar radiation, and from CHIRPS, we had precipitation. And how we process this? So we filtered for everything that was within a month of interest. Then we masked all the data for clouds and other problems that might be, they gave us like a quality band, and we used for filtering the bad quality pixels. And then we reduced those images to just one band that was like supposed like with mean or median aggregation. So you have just one band for the whole month. We stacked all the climate variables, and we did this from 2001 to 2022 in monthly timestamps. And finally, the last data source we used. So we had the climate variables, but they're not very good for extracting some information about drought. So the drought index, they were supposed to leverage the analysis of drought because they enhance some of those parameters that is important for us to do the analysis. So we extract from literature, there's these two best, they're important for using two different analyses. So the standardized precipitation evaporation index, or SPEI, is useful for short-term droughts. And we calculated it from CHIRPS and MODIS. And what is important to say that SPEI less than 2 is classified, -2 is classified as extreme drought, while the Palmer drought severity index is better for long-term drought analysis. We extract already calculated from TerraClimate, and a PDSI smaller than -4 is classified as extreme drought. Now I'll pass the word to Johanna to show some results.
Okay, so in this first section, we're going to look at general differences in precipitation and vegetation across these 8 regions. And so this graph shows all 8 regions and the precipitation time series across 4 years of monthly average rainfall. And what we can notice is they vary significantly, both in amount of rainfall that they receive monthly, and then also in the distribution throughout the year. So the regions 1 and 2 are deep in the Amazon. And you can see that we have this line of 100 millimeters, and that's a ecological definition for a dry month. So everything below that is considered a dry, we call it a dry month. And so you can see that regions 1 and 2 almost never cross this 100 millimeter threshold. They also don't really exhibit strong seasonal patterns of precipitation. Seasonality is something that Yihan will talk about in detail. And so they're consistently pretty wet regions. And then in regions 3, 4, and 5, we start to see some seasonality. And especially in region 5, we see that the dry season is true dry season. So during the dry season, this region transitions into really dry months with very not large amounts of precipitation. And then for the Cerrado regions 6, 7, and 8, especially the region A, they spend most of their time actually in these dry months. So another way to visualize differences in precipitation is to look at their monthly rainfall, mean monthly rainfall. And you can see that they're clearly across the precipitation gradient. Yeah.
Is there also a dual flood definition? So in the last region 8, there was a huge spike.
Mhm.
Is that because of flood and damage to the trees, or?
Oh, this one?
Yeah.
Yeah, probably not, because like those regions, they are so dry that the soil almost doesn't have water content. So that when the rain falls, it just like blow everything, because you have the flood when you have like continuous wet, and then you have like all the soil, all the space inside the interspace inside the soil, they are completely with water. And then you have the water going in runoff or accumulating on the surface. So
the flood analysis is separate from.
yeah.
Yeah, we did. Yeah, and we definitely didn't include flood analysis into this. It was a 2.5 month project, so. Right. Yeah, by the time we came back. So you could see a clear gradient of precipitation, but then we also looked at vegetation variations, and as expected, 2 biomes differ significantly. So for majority of vegetation things, we see 2 clear clusters. So we see moist tropical forests have much higher plant area index than the Cerrado forests. We see that they also have taller trees than the Cerrado. And here in this last graph, we calculated coefficient of variation, so standard deviation divided by the mean. And so we can see that in Cerrado, it's much larger, which means that the PI changes throughout the year much more compared to its mean. And it's essentially it reflects deciduousness of these trees. So during the dry season, it's one of their water adaptations. So during the dry season, they drop the leaves, and then during the water seasons, they regreen.
It's quite a surprising result, actually, I think. So
Is it?
I think you would expect to see, as you go along that gradient, it will just increase steadily. So it's quite interesting that this is a sort of stem, which will this Sahara.
Right. Yeah, it's almost like, oh yeah, none of these actually exhibit these patterns, and then but we keep seeing these clear 2 clusters in these 2. Yeah. And so if we put rainfall and PAI side to side, what's interesting is that if we look at these moist tropical forests, the first 5 regions, okay, they're across the precipitation gradient. They obviously they receive different amounts of rainfall, but then when we look at their plant area index, the first 4 are able to maintain consistently high and comparable levels of plant area index. The only time when we see a drop in vegetation is in polygon 5. And polygon 5 is special throughout our analysis. And another way to visualize this is we plotted 2 different ways of visualizing or calculating water deficit. So this is essentially looking at the difference between precipitation and potential evapotranspiration. And potential evapotranspiration is a measure of amount of evaporation that would exist if there was sufficient rainfall. And essentially here, the first graph is the ratio between PET and precipitation. And it should be less than 1 if the region is experiencing enough water for its vegetation needs. And it should be larger than 1. And the opposite is true on the right. there we just look at the annual difference in between PET and precipitation. And so as expected, the Cerrado regions are always in water or spend a lot of time in water deficit. But what's interesting is that region 5 is the one that's closest to this water deficit line, although we do see that region 4 also spends some time in water deficit. So one potential extension of this work, which we think would be pretty cool, is to look at this transitional region of water deficit and forests that lie within it, and look at plant area index of these forests, because we can find easily on a map. We have satellite data on precipitation and PET, so we can identify which regions lie in this transitional region, and then see if actually this is true. That once our speculation is that as moist tropical forests can maintain canopy denseness through a big range of precipitation, but once they near water deficit line, they start actually losing some of their vegetation. Yeah, go ahead.
These graphs don't defy data, it's purely existing waters and so on.
Yeah, I mean, this is possibly what we would also see with NDVI. I'm not sure. Yeah, with a leaf area index. Yes.
The other thing is, the reason I'm asking because GEDI is kind of different, there's the other arm.
Mm-hmm.
You could see the amount of forest that falls into, water deficit or not.
Mm-hmm.
Evolution over the last 80 years.
Yeah.
That might be very interesting. Is it getting dry or not?
Mm-hmm.
And then quick the answer. Very few of the countries for
Mhm.
they will be done, but they have great forest and evolution.
All right. And we can talk about seasonality.
Yeah. So now I will bring you into the analysis in more fine-grained details. So we decompose the time sequence of each variables into 3 components using the seasonality analysis, because we want to look into the patterns of these variables in more fine-grained detail. So as you can see in this plot, we decompose the time sequence into 3 components. The first one is a trend, which represents the long-term pattern of the variable. The second one is seasonality, and third one is residual. And we are especially interested in the seasonality component because it can represent the changing pattern over a certain time cycles. So here I display we displayed the seasonal components of both PAI and one of the climate variables, precipitation, for region 8. As you can see, both display very clear annual patterns, but also note that for PAI, which is derived from GEDI, we have relatively shorter time period to display because GEDI is only available since 2019. But for the climate data, we have a much longer time to do the analysis. So here we're looking to the comparison of the seasonality of vegetations. So we selected 2 regions. Region 1, which is the green circle, come from the Amazon. Region 8, which is the red circle, come from the seasonally dry tropical forests. So the first one is PAI, as you already heard. PAI is plant area index. So as you can see, the green line, which is the seasonal component of PAI in region 1, is constantly higher than those in the region 8, which means that it's dominated by a more dense forest. And also for the FPAR, which is represents the fraction of the solar radiation absorbed by the vegetation. Region 1 is also higher than region 8, means that the forests there usually have more active photosynthesis functions. And the curve in the region 8 has a more variable shape, which means that it has very significant deciduousness.
So what's the difference in the FPAR inputs versus PAI? Is it the speciality of the trees? There's different data going to calculating FPAR versus.
I think Felipe can answer.
So I think FPAR is calculated based on red and infrared band, and PAI is calculated based on GEDI data. It's like raw waveforms, so there are different ways of calculating.
Also, FPAR is actually not using GEDI.
No. It's from all this.
Climate
It's from
data,
all this.
yeah.
Yes, FPAR is from all this.
Yeah. So only PAIs come from GEDI actually.
GEDI, yes.
Yeah. So for precipitation and temperature, we also look into the seasonality of climate conditions of these 2 regions. Region 1, like from the Amazon, also has higher precipitation and generally lower temperatures. I know that like in region 8, the temperatures is also not only usually higher, but also more variable. So this indicates that the climate condition in the Amazon is usually more stable and more moist compared to the seasonally dry tropical forests.
What's this?
It seems to seriously the least smart things you've ever seen.
Yeah.
It's not working with the control and it's not showing on my screen, so.
Is there another?
The white screen?
Oh,
it's
okay.
Okay. Yeah, so now you have learned the climate and vegetation conditions of these two regions. We want to show you some more interesting findings. The first one is that we found a very significant, a boosting effects of precipitation on vegetation growth in both regions, like the region 1 and region 8. Know that it come from different climate and vegetation conditions. However, we found that the precipitation has a much stronger and faster boosting effects on the vegetation growth for those tropical dry forests. So this can be seen in the correlation coefficients. Here we correlate the time sequence of the PAI with the time sequence of precipitation happening in the same time, 1 month ago and 2 months ago. These are indicated by the subscript of the variables. So as you can see, we identify the strongest correlation number for region 6, 7, 8 in the precipitation happening 1 month ago. But for region 1 and 2, this can happen like either 1 or 2 months ago. So we think this represents the precipitation, the effects of precipitation comes faster on the vegetation growth, but also notes the absolute value of these correlation coefficients for region 6, 7, 8 are much higher than those in region 1 and 2. So we think the boosting effects is also stronger due to the climate condition in that region is usually drier. So this is a very interesting thing to think over the next few slides, like which factor can be the dominant factor here. So it seems that here precipitation is the dominant factor. And also know, like for region 4 and 5, the correlation coefficients can be negative. So this is related to another finding we want to show in this slide, which is region 5 that has been mentioned many times before. So growing up, if you don't know, it represents a long-term debatable question in Amazon, like vegetation can grow despite the dry in the dry seasons or not. So here, very interesting, we observe very typical growing up in the region 5. So you can see in the plot in the upper right corner, despite of the decrease of the precipitation, the vegetation still grow. And this is positively correlated to the growth of the radiation. And if we further look into like the vegetation and climate conditions of region 5 compared to region 1 and 8, you can find that although region 5 also experience more variable precipitation change and making it a more similar pattern to region 8, but in the most of the time it's still water sufficient. So we think that although region 5 still experience a more variable climate conditions, but during the dry seasons, when the water precipitation go down to the water deficit, the water content in the soil is still sufficient enough to support the vegetation growth and allow radiation, the increase of radiation to become a dominant factor to drive the vegetation growth. For the drought, so what we observed before, like these slides, are the correlation of vegetation growth to the general patterns of climate variables. We want to further look into their relationships with drought, like the extreme weather conditions. So here, we divide like each polygon into 4 by 4, namely like 16 squares for each polygon. So we have 128 points in total, and we aggregate the PAI for each small square over the time period, and we also aggregate the Palmer drought severity index for the time between 2014 and 2019 for each small square. And here we plot the aggregated PAI against the drought severity index. And as you can see here, we have very obviously two clusters in this plot, one in the upper right corner, another one in the lower left corner. And these on the upper right corners, they are all the regions from the Amazon forest. And in the lower left corners, these are regions from the seasonally dry forests. And it seems that for the clusters in the upper right corners, the abnormal water supplies won't significantly influence the change of PAI. But for the regions in the drier climates, they not only experience a greater degree of abnormal water deficits, and also PAI does appear to correlate with the degree of abnormal water deficits in these regions. So we further conducted the correlation analysis for these two clusters. So as you can see, for the Amazon for the seasonally dry tropical forests, is the PAI and the drought severity index are more correlated with each other. And for the Amazon forest, that's also correlated, but this is highly skewed by the points from the region 5, which we have analyzed before. If we don't have the points from the region 5, we doubt whether we will still observe like significant correlations between PAI and the
Region 5 is the one that David said he's surprised that it's not more smoothly interpolated in the deciduousness, right? Like that's one that should be in between both of them.
Yeah.
So that's probably the most uncertain one from the results.
Yes, yes, and if you pull it out for the Amazon, we then get no trend in the Amazon.
Yeah.
Yeah, if we just look at the regions 1 through 4, then there is no correlation with.
Yeah, or if we average for the whole region and have just 1 point instead of like those different squares, you don't have correlation at all.
No.
But like whatever we do on SDTFs, you always have this trend, significant trend of increasing, yes.
I guess it's worth mentioning that they're also not in order. So the blue one is actually the one that says it experienced the most, it's region 3, for which it says it experienced the most drought. But that's also the one where we're missing a lot of data for with GEDI. So that's also worth mentioning.
Yeah, so now I will hand over to Yvonne again.
Yeah, so well, we really like our forests, obviously, but we did secretly hope that there was a drought in the period of 2019 to 2022 that we could analyze with GEDI, because ideally we want to see measure PAI before the drought and then after drought and be able to compare those effects. And so we did calculate SPAY index, all kinds of SPAY 3, SPAY 6. So usually SPAY is calculated as a sliding window of months. So when we say SPAY of 3, that means how dry was those 3 months compared to what usually that region experiences in 3 months of rain. And so we looked across, we focused on the moist tropical forest because we wanted to know, okay, they experienced a lot of precipitation. What would happen if they experienced less? And we found that region 2 did experience 2 droughts. So we were, that it wasn't a lot, but you know, it was something. So it experienced actually 2 droughts, one in 2020 and one in 2021. And so then we took a look at what the vegetation response looked like, our weighted average time series during that period. And so at the top, you can see SPAY of 12 months, then you can see SPAY of 3 months. The SPAY of 3 months is more extreme, which means that this was a relatively short-term drought of 3 to 6 months. And you can see that the 2020 drought is more extreme than the 2021 drought. If we look at the precipitation at the bottom, we do see the decrease in precipitation during those periods. But interestingly, this is region 2. So this is the region that's used to a lot of rainfall. So when there's a drought in this region, it doesn't even go into the dry month. So it's not really dry, it's just dry for what this region is used to, right? But it's still like above this 100 millimeter dry month line here. Yeah,
In region two or Manaus? Manaus is region three, right? Or you're north of Manaus?
we would have to go back to the map, so maybe
Yeah,
hold
I-
that
I-
question for later.
I don't think so. I think like region two is like on the north of the Amazon state in Brazil. So it's like supposed to be like in the core Amazon. I think none of those polygons, they are near to big cities. Like I think because when they selected, they were like trying to select regions that were like far from
It's
people.
like the mega 2021 flood was in the Manaus Basin.
Yeah.
Wasn't it?
Hmm.
Yeah,
That was
so
like the biggest recorded for it.
yeah, so something that like worth saying, like during the last 4 or 5 years, South America has been in a lot of influence of La Nina. And which means La Nina that is you have abnormal rain patterns, so you have increased rainfall. So all the data that we have for GEDI is being on like compared to the average mean, we have more rainfall than usual.
Maybe we
So-
should have studied floods.
Yeah.
Flood effects.
So like this year, it was supposed, like after a long time, El Nino was supposed to go back to South America. So we are probably seeing the next years to see more effects on drought because probably it's reducing the rainfall for the next years.
So the spade 3 is going really very negative.
Right.
-2 means that a really extreme event.
Yeah,
And it's not down to rainfall, so it must be increased air temperature. Driving evapotranspiration.
we did.
Must be one of those two things. It's not rain.
I mean, I think this is pretty low rainfall because if you remember, region 2 rarely experiences rainfall that's even close to 100 millimeters. So that's what I'm saying, like this is relative to what it's usually. A SPEI is a relative measure for a particular region. That's why it's also very difficult to compare SPEI across regions because it's not an absolute measure of dryness. It's just a relative measure for this ecosystem. Yeah.
It's quite clever approach. I was thinking. It's not looking at rain patterns across regions, saying, okay, this part.
Right.
Is it an extreme?
Right, this would be a flooding event in Cerrado. This is actually a drought, extreme drought in the Amazon. So that's very interesting. And I mean, if we look at the time series, unfortunately, we discovered all this maybe 5 days before our deadline. So we didn't have much time to like dive in when we would love to do that. But we noticed there's a drop in PAI in the 2020 drought, but then there is a really quick recovery, partial recovery that we'll see that follows. And then in the second drought, we again see a more regular decay of PAI, and then it continues this loss. And unfortunately, then we didn't have more GEDI data available because there's always a delay in Cairo. So we don't actually know if this region recovered, and we would love to take a look and see if the PAI has recovered. But we could have two potential hypothesis from this that we should further test. So one is that the rate of loss of PAI is proportional to the extreme of the drought. So there is a more sudden drop in PAI during the more severe drought in the first period. And then the second one is that it's possible that subsequent droughts inhibit regions' ability to quickly recover. So in the first one, it managed to recover quickly, but then in the second one, it didn't. But there could be also other factors in play. And then Felipe also pointed out that SPEI 12 is only starting up here to kind of go into the blue zone. So it's possible that, you know, there's still like long-term dryness components that are playing into the forest recovery.
Bill Andrick's hypothesis was successive droughts for North American forests, wasn't it? Saying that on the third drought or higher, the forest would just die off suddenly.
I see.
Versus 1 or 2, but that was only North American forests.
I see, interesting. Okay. Okay. And then we also wanted to take a look, because we have GEDI and we have opportunity to look under Canopy. And so there, we wanted to see like, okay, when a drought happens, is the canopy or an understory more affected? Of course, this is a very simplified picture of a tropical forest. It has actually many layers, but let's call them a canopy and an understory for simplification. And so there seem to be two prevalent theories in ecology. Like one is that the canopy will be the one affected because it's more exposed and under canopy is protected. And then the second one is that under canopy, because it's smaller and younger trees, they don't have big water reservoirs, they will be the first one to die off. So let's vote. Which one do you think? Who thinks the canopy will be more affected? David, that's not fair. You knew. Does anyone think under canopy? Does anyone think under canopy would be more affected? Well, before we show you the results.
a little bit of graph.
Yeah, I mean, ideally, what we want to do in this situation is use what Amelia is actually developing right now, which is find coinciding GEDI shots and then take a look at what the PI looks before and after the disturbance. But we didn't have time to really do all that GEDI shot matching. So we did the second best thing, which is roughly make sure we're sampling from the same region. So on the left, you can see all the shots that we had. The blue is 3 months before the drought. During the drought is 3 months in red, and then the after drought is 3 months in green. So we at least limited them to this like kind of overlapping region in the middle, so that they are kind of sampling from, they're not exactly overlapping, but they're generally sampling from the same areas. I guess it's worth noting that even without this or with this, we consistently got similar results. So, but we tried to filter. And so this is what we observed. So this graph, people have complained that it's complicated to understand, so I'll try to explain this well. So on the x-axis is the plant area index, and on the y is height. Tom suggested to put height on as a y. And so each of these points, so this point represents PAI in the heights of 0 to 5 meters. And so this one then is PAI in 5 to 10 meters vegetation. And then you can see that the highest PIs are in trees that are to 10 to 15 meters, like those levels of vegetation, et cetera, et cetera. And so the blue line is what we've observed before the drought. I mean, this is just the mean of the whole distribution. And then the red is during the drought. And then we see a consistent PAI loss in the canopy, with the understory being largely unaffected.
This isn't a portion of loss, is it? It's the absolute amount.
This is the absolute amount. Yeah. And then when we look after we see going back up after doing the after. I mean, this needs further analysis. This was just, but definitely it seems to indicate that the majority of forest was affected in the canopy, and we don't really see much happening in the understory.
Height there is the RH95.
No, the height is, so GEDI returns this vertical PAI product that gives you an array of PAI from 0 to 5, PAI from 5 to 10, PAI, and just kind of an array of these things.
Slices and then integrate inside the slices.
Exactly, exactly. Although done for us, the processing of this data was a bit of a pain, I have to say, like the vertical with the arrays and, yeah, that's why it took us so long to even look at this, because PAI and canopy height was much easier to work with. But now we know how to do it. So
Bit unfair to the understory, right? For your original questions, because there's so much less land area cover there in the first place. That it seems to have lost proportionally roughly the same.
Oh, you mean like, yeah, look at it as a percentage of, that's a good point. Yeah, that's why I think this can be definitely much further explored. Yeah.
But the understory is growing.
In the second,
In the first one.
Oh, it's true. Yeah, actually, see, yeah.
Yeah.
I mean, but yeah, to be fair, this is just looking at the mean, so I don't think it's, you know,
The
yeah.
understory is getting more light due to the loss of the.
I mean, now we can speculate as to could be. No, the red is during the drought.
Yeah, so during the drought, there's less PAI than before.
There's more in the canopy, and less in the canopy. I mean,
Yeah, the red is the right of the blue.
yeah, see, the red is here greater, because this is PAI.
That's right.
Yeah.
The drought is being a bit of not having much rain, and so there's less water coming from the soil, but actually the major impact is that it's usually hotter. The hotter air temperatures drive evapotranspiration, and there's an exponential relationship between temperature and evapotranspiration. So what you probably see here is that the top of the canopy, where it's driest and hottest, is the one where there's the most stress on the plant. That's where it's the leaves and the leaves. The bottom is still moist. Damp or still
Yeah. We found one paper that actually have similar results, but in the field. They didn't use GEDI, but this is, I think this is cool because a lot of people are coming up now with papers from GEDI, but most people are still just looking at plant area index and canopy height, and for whatever reason, not a lot of people are looking at the vertical, maybe because it's hard to work with it. But no, it's not that hard, but not many people are actually publishing anything related to the vertical structure, which seems to be one of the biggest appeals when it comes to GEDI. So, yeah, so.
So there is more GEDI data which you didn't process in your project. What is that? So the PAI recovery could look at a bit more
Right,
time. Would you?
right, yes.
That'd be interesting.
Yeah, yeah. I mean, I think now we actually could also get GEDI data for further into the future, because there's like a 4-month delay. Is that what you said?
It
Yeah.
was supposed to now to have, because they took off the GEDI now in January. So they are retiring like for a short period, they are putting back. And there's a 4 months of latency. So probably this month they will release the last data that is available. It is January 2023. So it was supposed to be on the UNB website, but Amelia can give us update on that because I'm sure you know about this.
Yeah, and that's it. Thank you. These are some of our summaries, but we can take questions if you guys have, and just wanted to thank Amelia and Charlotte once more for being with us along the way and helping us. So yeah, that's it. Thanks.
Okay.
If you have time for any questions, any more questions?
Wow, 1:55. We thought it was gonna be a 25-minute presentation, but I guess we can talk a lot. Did you guys notice Felipe custom made each of these trees on the slides? And you see the yellow ones represent Cerrado at the bottom, you see the little ones? And these are the, where's the tropical one? Yeah, yeah, no, this was all, yeah, hard work. That was on car, yeah. Well, you guys, yeah. But
I think it's very good. I think part of the reason why some people are upset is because there's no machine learning or AI in there. It's all just because the results are, very, very good. I don't think from a foreign science perspective, we're feeling shortchanged.
Okay, I'll buy. How do you think you could best apply machine learning to?
I think something that would be like really applicable if we could some way to model, which is like really hard, like some way to find some machine learning for a model and take the data that we have in a long period and try to model some of the parameters tracked by GEDI. And then we have this wall-to-wall maps would be very useful because it's like because the orbit of GEDI is not regular. So you cannot guarantee that the same point will be sampled like never again. So it changed the orbit and you don't have the same point sample, you don't have this wall-to-wall maps or have information in every pixel. So having these maps with some good accuracy, it would be nice if machine learning can provide, because if you have like those maps for like everything and like in regular regular periods of time would be really interesting. But we gave up like this on the first week because we realized that we wouldn't be able to solve this problem in 2.5 months. So.
I mean, just talking to us in the model, I think you and I discussed this a little bit. What you've done is to analyze all the data, right? What you could do is to take away 20% or something as your test data and then train a model using AI on some fraction of it that's going to relate, for example, PAI or let's just say PAI and solar intensity to the drought index and solar intensity to the plant index. It could be done as a multiple regression, but you could also do it in a machine learning task and then test that model on the test set. So you could, in fact, do learning of the parameter space from, and the answers are given that, what fraction of growth is to solar intensity, what fraction of that goes to water, right? And so, and if you did that properly, then you should be able to answer, you should be able to build a model that will work for all regions. Not just separate regions that we have a single unified model for all of it. Right? So that could be one thing to possible.
I was wondering about in the beginning, the pricing result that they mentioned about how the change in deciduousness in different classes and it's kind of a step function, but not a gradual change.
Yeah.
I was just wondering if it could be because you're defining this in terms of change variation in PAI, whereas maybe there's a gradual change in the forest composition so that there are more and more deciduous species, but up until site 5, maybe they're still like they have different patterns of leaf shedding, so that as a whole, the PAI doesn't vary that much, but maybe more and more species are shedding leaves, just maybe in a way that's still globally complementary, so that you don't observe a clear structure change. Whereas when you transition into Cerrado, then overall most species are really shedding leaves at the same time, so that it becomes observable.
Oh, you mean like maybe they're shedding at different times?
Yeah, just or maybe each species may be responding to drought signals slightly differently, so that it's the signal may be a bit smooth out.
We talked with Ton about deciduousness, and he showed us some articles saying that like in this tropical forest, it's not something normal. Like you can have like very old leaves in tropical forests that can have like decades for falling. So I don't know if we're supposed to see like any pattern of deciduousness in the Amazon. At least we wouldn't expect this, what previous people have been reporting about leaves in those forests.
The classic stories as you go along the humidity gradient, you have no deciduousness or very little, and then as you go along the very, very biggest trees, it becomes deciduous, and as you go drier and drier, then more and more of the trees become deciduous. So that's all I would expect to see personally, but we're not seeing that as a I don't think there was data for that.
Yeah. There was.
You said there's like initially chosen regions, I mean, these regions. There are many more regions that are either side of region 5. If you have a transect, right, that goes from Cerrado
Right.
to
Then it would be cool. Yeah, because we could take a whole JEDI trajectory one and like examine it. Yeah.
Could see.
Northeast.
Mhm.
Get a transect, go on to that path, or I guess they go.
Yeah. Yeah.
You choose a longer pathway.
Mhm.
Get more points probably in the what's region by region with the transition regions, we wouldn't have this arbitrary contribution.
Yeah. No, this was the 8 regions was just easier to deal with in terms of data quantity for this. But yes, absolutely, we could do this whole analysis of the entire region essentially. Just wanted to add something. We noticed this pattern also in canopy height. Region 1 and 4, like if you plot PAI and canopy height, region 1 and 4 go together, and then regions 2 and 3. But we have no idea why, because 1 and 4 are very different in every single regard. And yeah, but although this is like RH 100, so maybe it's not that reliable, but it was still a clear.
Show the map.
Like here, oh, a map. A map.
RH 100 is not good.
Yeah.
95, but RH 100 is good.
Yeah, but it's just like, why did they make JEDI data so annoying to be like, it's RH metrics are all in, what is it? L2, Amelia's laughing. It's like RH 195 and all of them are in L2B, right? Or yeah, and PI is in L2A. And then you have to download them completely separately, or the other way around. Yeah, they're in separate, and yeah, it's just very difficult.
So you asked about Manaus. So if you look to the Amazon River, you won't be able to see, but there's Black River that is going down, so it's on top. Can you see the Amazon River?
Yeah.
So it's on top of Manaus.
Yeah, so that mega flood in 2021 was right there, right, on the Amazon River. Because that was like the biggest flood in decades, I thought.
So then region 3?
Yeah,
really
you see it, yeah.
Well, 1 and 4 is where that has the tallest trees, 1 and 4.
Always where, close to where Eric found that. We did all 3 of them.
Interesting.
So it's actually in the dry history. It's still wet, is that 4?
Yeah, but 4 and 5 have the like clear seasonal. They're actually very similar in precipitation, 4 and 5. Yeah. But anyways.
Okay, I think we need to start.
Yeah.
Thank you.
Thank you.
Where's on